Shall I start?
Yes.
So, good afternoon, everyone. It's a pleasure to introduce today Kristen Dag, who is going to be talking about ultraluminous X-ray sources in extragalactic globular clusters. Kristen is a Quebec Nature and Technologies postdoctoral fellow at McGill University since 2020. She obtained her PhD in astrophysics in July 2020 from Michigan State University and her Bachelor's of Science in Physics at the University of Michigan, Dearborn in 2014. Kristen, it's a pleasure to have you here. Please, the floor is yours.
Thanks. Thanks for having me. I'm very excited to talk to you all about what I think are some of the coolest sources. And so by the end of my talk, I hope that I can, have, informed you a little bit about what they are and what we know about them and why everyone should care about them. But to start off, of course, I'm going to focus a lot on compact objects. So, some quick definition and visualizations of them is that when stars die, they can turn into compact objects. So this means they can be either black holes, neutron stars, or white dwarfs. These compact objects have some really, really extreme gravitational forces because of their high density. And that means there's a lot of exciting physics happening with them. So I'm mostly going to talk about black holes. I will talk a little bit about neutron stars and a little bit about white dwarfs by the end, though. So, I think there's a lot of reasons why we want to observe black holes, but, unfortunately, the definition of a black hole is that it's an object that doesn't emit any light. And since, astronomers primarily search for things using electromagnetic waves, this is a problem. Luckily, black holes interact with things that have light, and we now can detect gravitational waves. So we do see them. And so this is really, really exciting because that means that, as you know, we've been able to actually image a supermassive black hole. And thanks to LIGO-Virgo, we've actually detected on the order of hundreds of stellar mass black holes merging with each other. So this is, great because that means that we have information on objects that are 5 to 100 solar masses. And then also we know about black holes that are, millions to billions of solar masses. There's also this, this is Rufus, by the way, he's my parrot. And so we don't have any information about this, in-between category of black holes, so thousands of solar masses that we call intermediate mass black holes. But they're, very important for a variety of reasons, both cosmological and also for future gravitational wave detectors that are going to be launched. But we have no observational evidence for them yet. We have, some leads, and it's not great. And then the other thing I want to touch on a little bit more in detail is talking about gravitational wave detections. So again, we see when we have two black holes merging into each other, they produce gravitational waves that, we are now able to detect, which is pretty fantastic. But one of the things that's weird is that we are detecting more and more black hole binaries merging than, we ever thought was possible. And so that means that there is, this quest to understand how these objects could have formed. So I will talk on this in a little bit more, but I wanted to, introduce that now. So as an observational astronomer who works on compact objects, I am required by law to show you this artist representation of an X-ray binary. I love this picture because it has everything. So you can see, somewhere in here we have our compact object, our black hole or neutron star. It is friends with this star over here. And because this one is so much more dense, it steals matter from the star. And then this inflates and fills its Roche lobe. And of course, your star is spinning. And so that means when the matter is accreted, you have conservation of angular momentum. And that matter forms an accretion disk around the compact object. And this gives off X-rays. And that's what we're able to study. So I should also say right now that my focus is primarily on things that are outside of our galaxy and on the order of, I would say, like 20 or so megaparsecs. And so that means that a lot of the detail in this artist representation are not actually things you can observe. So for right now, for my talk, just, focus on the accretion disk and don't ask me what a hotspot is. Another important thing I have to introduce is the Eddington limit. So the Eddington limit is a back of the envelope calculation from 100 years ago, where Arthur Eddington said, we know that we always have gravity pushing in on us. And in the case of stars, we have radiation pressure pushing outwards to counteract gravity. So what happens at the point where the two balance each other? And so when you make a lot of assumptions and you set these two equations equal to each other, what you find is that if you are an object of a certain mass, there's a maximum luminosity that you can give off that is a function of your own mass. And so this magic number is 10 to the 39 ergs per second for a 10 solar mass black hole. This is hugely bright. So for context, the sun's total X-ray luminosity is about 10 to the 27 ergs per second. And typical X-ray binaries within our galaxy, if they're considered faint, they'll be 10 to the 33 ergs per second. And something like 10 to the 36, 10 to the 37 is considered bright. So the objects here are several orders of magnitude above that. And so, of course, there are so many assumptions that go into the Eddington limit that it's not at all a hard and fast rule. But the way you can think about it is that if we see something that is not a supermassive black hole that is, about this luminosity or brighter in X-rays, that's interesting. So like I said, the Eddington limit is not a hard and fast rule. It's a little bit like a speed limit. There are signs saying that you're not supposed to go above certain speeds, but some people do anyway. And so in the case when that happens, there's two scenarios that we can think about to interpret this. And so the first one is that, okay, so we said the Eddington limit was for a 10 solar mass black hole. If we bump up, the mass and say it's 1,000 solar mass black hole, then that luminosity limit goes higher, and it's not surprising that something that's 1,000 solar masses could have a luminosity of 10 to the 39 ergs per second. And then it would just be accreting in sort of like a normal regime of physics. And then the other option, which I think is a lot cooler, is that you could have an accretor mass, so either a black hole or a neutron star that has a mass of less than 10 solar masses, but it's, the accretion physics is such that it has ways to get around just the assumptions of the Eddington limit. And so one of these ways that has been people have thought about are outflows. So of course, we know that supermassive black holes can have outflows. This is an artist's representation of one of those. But the general idea is the same, as that, something happened in your X-ray binary where you have these winds blowing stuff around that can also be accreted onto the compact object, in addition to the accretion disk, which gives you extra avenues to create extra luminosity beyond just the disk. So in terms of observations, the ultraluminous X-ray sources were not, studied in astronomy, I would say, until 1989. That was when the first paper on them came out. And they're really mysterious. And so the other thing that's, worth pointing out about them is that for the most part, they're studied and, found in young star-forming galaxies like this one here. And so you can see this is a nice spiral galaxy. It's got lots of star formation, and it's got a ULX right here. But excitingly, ULXs can be in globular clusters, and these are really, really different environments. So since 2007, we have found about 20 ULXs associated with globular clusters. And so sort of for comparison, I think the numbers on total populations of ULXs and other types of galaxies, which are not super complete, is about 600 ULXs. So this is a very, very rare subset of them. But it's very, very exciting because globular clusters are amazing. And the idea that we have, these X-ray binaries in there that are going above the Eddington limit is very exciting. So one of the things that makes globular clusters special is they are dynamic. So I didn't appreciate this until I started keeping bees a couple years ago. But when you look at this image of all of these stars in the cluster, these are all moving and interacting with each other, just like bees interact with each other and move around. And this allows you to create very, very unusual X-ray binaries. And in particular, there's something called preferential mass exchange. And so when you have two objects in a binary and a more massive object passes nearby, they will interact with each other, and the less massive object in the binary will be swapped out with the more massive object. So this means that just because two objects are in a binary at some point in their lives doesn't mean that they will stay together forever. And so I have come up, with this way to keep them straight. So star-forming ULXs, or ULXs in the majority of ULXs, I should say, are kind of like my chickens. They were born together. They have never been around other chickens, and they prefer each other's companies. So they are associated with young systems, and a consequence of this is that you could have high mass donor stars. The ones in globular cluster, on the other hand, they've undergone dynamical evolution. They are associated with old system because all of the stars, more massive stars in a globular cluster have died off, and they have to have low mass donor stars. So I see them as, like Statler and Waldorf, where they had to go through a whole theater of Muppets to find each other, meet each other, and become friends. So I promised I would talk a little bit more about LIGO. And one of the really, really exciting things about LIGO is that we think that globular clusters can actually explain a significant fraction of the rates of black hole binaries that have been detected merging. And this makes sense because we know that globular clusters should be black hole factories because all of our massive stars have died and turned into black holes. The problem is that for the past 50 or so years, from a theoretical standpoint, everyone said, of course you're going to have your black holes in your globular clusters, but when they, explode and turn into black holes, you're going to have natal kicks and then also gravitational interactions that boot them out of the cluster. And then they would, of course, compound this and say, we don't have observational evidence for black holes and globular clusters, so it could be that they all get booted out. Now, newer simulations and observations are showing that this is not the case. Of course, the whole problem here is that if you want to show that globular clusters are a really, really excellent birthplace to form black hole binaries, then you need to find observational evidence of black holes and globular clusters. So what we know about black holes and globular clusters from an observational standpoint is not that much, as it turns out. So we didn't have the first observational evidence for a black hole in a globular cluster until 2007. And then as of now, we have about 7 black hole candidates in galactic globular clusters. And then we have, I think it's now 2 or 3 confirmed black holes in a globular cluster in NGC 3201. And so this is about less than 10 black holes in globular clusters for our galaxy. Now, there's another problem with our galaxy, which is that it only has less than 150 globular clusters, and they don't have the population of these globular clusters is not really indicative of globular clusters, as a genre. So for example, and this is why I tell people I don't like the Milky Way, is that if you go to any other galaxy out there, you can have hundreds to thousands to 10,000s of globular clusters in a system. So a galaxy like M87, for instance, has over 10,000 globular clusters. And so those are the kind of galaxies that if we really, really want to understand, black holes and globular clusters as a population, we need to look at those other galaxies. So the next question, of course, is how do we do this? And so the answer is we do this with every telescope we can get our hands on in every wavelength that we can possibly use. So I will talk about using most of these telescopes in the talk, but I'm going to mostly focus on X-ray and optical for a large part of it. And so specifically the ones that I mainly use would be Chandra and XMM for X-ray, Hubble as well, and then 2 ground-based telescopes, SOAR and Gemini, which are both in Chile. So the sort of practical way that we find ULXs in globular clusters is that we will take something like a Chandra image and we will run a point source detection algorithm on it to select out the brightest X-ray sources. And then we will use data from, for instance, Hubble, and then we can get globular cluster catalogs out of Hubble and cross-match those 2 with each other. And because even though we're going to, fairly far outside of our galaxy, because ULXs are so bright, we get quite a lot of, a fair amount of information on them relative to the distance. So this is an example of what it looks like. This is a Hubble image of NGC 4472, my favorite galaxy. And so what you're seeing here, this thing that looks like pictures of globular clusters I've shown in the past, this is actually the host galaxy. And a lot of these little dots here are globular clusters. And so the green regions are from X-rays. And so those are regions where we detected X-ray sources, and then we cross-match them to this Hubble image. So this is really exciting because that means that we can use both X-ray and optical to study and characterize not only the behavior of the X-ray sources, but to also learn things about what kind of globular clusters can host these sources. So something I want to emphasize here, if it wasn't clear from the last one, is that from now on, even though I've shown you this beautiful, beautiful picture of a galactic globular cluster because it's pretty, when I talk about globular clusters from now on, they're going to look like this. They are point sources. So that's, you know, sad in one sense, but exciting in another sense, because we can do optical spectroscopy of the entire cluster, so integrated light spectroscopy, and we can learn about, you know, the populations of stars in it. I'll show a few spectrum and talk about what these can tell us. So this is an example of the globular cluster spectrum. This is from Gemini, and so this is any sort of, you know, features in there are, you know, intrinsic features to the globular cluster, and we can model these and fit these, and we can learn about the age of the cluster. We can learn then we can measure the metallicity of the cluster. This also gives us a handle on the distance, because when we know that our X-ray source is hosted by a cluster, that cluster is associated with the galaxy that we have fairly good distance measurements for. And then we can also search for like absorption or emission features beyond the globular cluster continuum. So here's an example of what that would look like. So this spectrum is of a different source that is weird, and we don't know how to explain it. But what you're seeing here is all of these little squiggles are features of the globular cluster continuum. And then rising above the globular cluster, we have these emission lines. So these are O3 and N2. These are completely forbidden transitions. So as a non-atomic physicist, I'm going to do my best, you know, to explain this to you. But what it means, I was really excited when I learned about forbidden emission lines because they sounded really cool. But what it means is that there's only specific conditions when they're allowed to transition. And for the ones that I'm talking about today, they can only you know, have transitions and emit light if they're low density. And so this suggests that when we see these emission lines, that's some kind of marker of accretion and maybe even outflows with low density. So the artist representation that I showed earlier in the talk, where we had you know, kind of material swirling around the compact object that was being, you know, hit in some way, is an example of the physical mechanism behind the emission line that we see. And then the other source that we have an emission line for is my favorite source ever. I love this source. It is called RZ2109. And so this is its spectrum here in optical. So what you're looking at, this black line is actually like a model fit to the globular cluster continuum. So what the globular cluster would look like if it didn't have this giant oxygen emission line right here. This is a doublet. So there's a 5007 doublet and 4959. And then there's a 3-to-1 ratio set by atomic physics. This is usually a line that's seen in planetary nebulae, but this is extremely unusually broad. And so we know that there's some object accreting here. And the object that's being accreted is giving off a ton of oxygen. And we know because we fit the globular cluster continuum, we don't have excess hydrogen in the system. And so that means that we have an object that has a lot of oxygen and no hydrogen, which could be a carbon-oxygen white dwarf. So that would put this object in the class of objects called ultra-compact X-ray binaries, which are very, very, very strange and exciting objects. I don't have like too much on them, but if you want to ask me more about them after the talk, I love them and I would be happy to talk about it. Now, the other thing about this line that's weird is that we have been monitoring it over time using SOAR. And we see that the not just the shape of the emission line changes, but the intensity. And so you can see that we have this core that where we have, you know, the amount of flux in there has changed over time. And then we have these two wings. And, you know, for some of them, the wings are even. And then this one, this spectrum, this wing has a little bit more in it. So another way to visualize it is this is just adding up the equivalent width or the flux in each of those components that I marked in the previous thing. And you can see that it's been going down until here. And so I think this must have been, I think, in 2016. And I remember taking this spectrum and analyzing it and being sad that, oh, we're not going to see emission anymore. And then going back, I think it was the next year, and then it got brighter. And so this is really, really hard to interpret. But one of the things that's really nice about the variability in oxygen is that we know that this has to be associated with our X-ray binary, and it's not, for instance, like a nova happening serendipitously in a cluster that also has a bright X-ray source. But this also allows us to place size scales on the amount of oxygen in the system. And we know that has to be a nebula because it's a forbidden emission line. And so we can actually make size estimates of how much oxygen is in the system. And one of the things that's really exciting about it is that it's, so I'm going to observe it in April of this year again, but when I observed it last year, we still saw, the emission lines here. And so that means that we've seen this on for, I think, almost 20 years at this point, which is exciting. So now to talk a little bit about the X-ray. So I'll mostly be talking about Chandra. This one's Chandra, and a little bit of XMM, but those are the main two I use. So like I said, there's 20 sources beyond the one that I just mentioned with the optical emission line. And then we've looked in about, I think it's 5 or 6 galaxies now. This is not quite up to date. And these are X-ray images of what they look like. And so you can see that the center of the galaxy is bright in X-ray. And then we have a lot of, little dots here, which are all X-ray point sources. And then these ones in particular are the bright X-ray point sources that matched up with a globular cluster. So one thing about X-ray photon collection and why one thing that's really nice about doing X-ray analysis is that unlike an optical telescope, so for an optical telescope, the light comes in and gets focused to the mirror, and then it makes its way over to a CCD. And so if I wanted to know about the location of a source on the sky, I would take a snapshot. If I wanted to get information about time variability of the source, I would have to take a series of snapshots. And if I wanted to do spectroscopy, I would have to put in a slit and then align the target in the slit and take an exposure that way. The way X-ray telescopes work, so you can't just directly, use a mirror to focus the X-rays into the CCD because they're too high energy and they would pass through. So there's this series of hyperbolic mirrors where the X-rays come in and then they actually get downscattered. And so when they do that, they lose energy so that they can be, detected by the CCD. But the angle that they come in at is, that information is saved so you can get the energy of them. So that means that you can get the location on the sky of the X-rays. You can get the timing of the arrival time of each photon relative to the others, and the energy of each photon. And so one of the things that you can extract out of an X-ray data set is the X-ray light curves. And so X-ray variability, even if we don't necessarily know what drives it or how to model that, it's very useful diagnostic for the physics of the system because, of course, a source where the number of photons coming in over time behaves like this is going to be very fundamentally different than a fun source like this, where it could, flare and peak and then go down again. So some of these globular cluster ULXs can vary in X-ray within hours. So for example, this source dropped by, I think, 3 or 4 orders of magnitude over about 4.5 hours. So this is highly variable. This is another source that does that. And then this source is interesting because it shows, some variability. But then sometimes when we've looked at it, we don't see it doing anything interesting. And then the other thing, of course, is their long-term behavior. So this source was detected in Rosat in the 1990s and in Chandra up until 2003. And then we haven't seen it in X-rays since. Whereas this source, which is highly variable, we've been observing for the past 20 years. And when we catch it in this state, we can, see it in X-rays. So it's a very, very weird source that we don't know how to interpret yet. And then of course, other globular clusters just don't really vary within an observation. And like, so we did like do analysis of these and showed that anything that could be construed as variability in these is actually just due to instrumental noise. And so this is, the majority of the sources don't vary within the observations that we can tell. But what's exciting to me is that we have a very small sample here. We have 20 sources, but they don't all behave the same. And so that suggests that we have, sort of a diversity of physics happening here. And so maybe we have, different donor stars or like different compact objects that are accreting in different ways, or like different masses of compact objects, for example. And then the other thing is that they can vary long-term or not at all. So this source is kind of mind-boggling to me because like these two data points were taken a week apart and there's, a big jump here in terms of X-ray luminosity. And then other sources, like when we plot their X-ray luminosity over time, they just, have a value that they like to hang around and not really change. So about half of them vary on the timescale of months to years, and they don't vary in the same way from each other. So at the beginning of Anna Karenina, Tolstoy says, happy families are all alike and unhappy families are unhappy in their own way. And I think my version of that would be to say that all non-variable sources are alike, but every variable source is variable in its own way. And it's really, really exciting to see this level of variability because this could be, potentially connected to all sorts of, exciting transient physics that we just don't understand yet. So I mentioned X-ray spectroscopy a little bit. So because we know the energy of all of the photons, we can make an X-ray spectrum. This is, on this axis, you would have the energy, and then you would have the number of photons at each energy. This is, very oversimplified because you have to fold in basically properties of the detector and things like that. But we can model the shape of the spectrum because that tells us things about the physical emission mechanism. So these are a couple of spectra. I really like these spectra because they both came from two different sources nearby each other. So these are all taken in the same data set as each other. And I think it really shows you, the different spectra that you can get. So for example, this orange one that I've put this little cartoon yellow line over is best modeled by like a black body disk. So this is Wien's law that you learned in physics a long time ago, but with some prescriptions made because it's, now an accretion disk. And so this is thermal accretion that is from the disk itself. The other source in here, when astronomers don't know how to fit things, they fit things with power laws. So this has been fit with a power law. And there is, even though power laws are just, a thing that don't necessarily have any physical ties, this may be due to inverse Compton scattering, happening, at this part of the compact object. But so, when I talk about the rest of my spectra, I am going to focus on the ones that are modeled with the disk because that's more physical and I think it's easier to interpret and make sense of. So there's a question we can ask here because not only do we have the shape of the spectrum, but we have the shape of the spectrum over time and we have the X-ray variability over time. And so we can ask, do these globular cluster ULXs show spectral variability that corresponds to changes in X-ray luminosity? So to do this, we can make this plot. So on the axis right here, we have the X-ray luminosity. This is 10 to the 39 ergs per second. This is 10 to the 38. And then on this axis, this is what I'm calling the characteristic spectral parameter, which in the case of the accretion disk model was the inner disk temperature. And this is in keV. And so what you can see here is that there's this little clump of sources that are weird, and then there looks like other ones have trends that pop out. So in particular, this one is very interesting because you can see for the most part, it seems that as your temperature increases, so does your X-ray luminosity. And this makes sense. It ties into physics, like the Stefan-Boltzmann law that says that. And so a lot of galactic black holes also follow this trend. These two sources, on the other hand, are strange because the X-ray luminosity and the temperature don't have a correlation with each other. So in the case of this purple source in particular, the temperature is always about 0.2 keV, but it spans, quite a large range of X-ray luminosities, which is really strange. This source is about 0.4 keV. It's a little bit more spread out, but for the most part, it doesn't really seem to change. The temperature does not really seem to change with the luminosity. So, and then the other thing that's interesting that separates them is that these sources, the fits are for the most part, below or well below 0.5 keV. And this source over here, hangs out above 0.5 keV. So there's also a temperature separation. So now that I've, walked through this, very messy and confusing plot, I think the next question is, can we tie this into the optical emission I showed earlier? And, luckily for us, I do have optical spectra for all three of these sources. So I can show this one spectrum first. This one is just the typical globular cluster spectrum, nothing interesting going on here that I showed earlier. So that's kind of sad. But we still have these two spectra left, the really exciting one that is oxygen, and then the other one that's weird, and we don't know how to explain it yet. And those belong to these two sources, which is really exciting. So we can put this all together and make some very I think slightly hand-wavy claims about what could be going on here, given the evidence. And so for this one, it might make sense to interpret as a more massive black hole that's accreting below the Eddington limit. And then in that case, it's not really surprising that it behaves like a galactic black hole X-ray binary, because it's not, it doesn't have any unique physics beyond, just accreting normally from its friend. These ones, on the other hand, one possible explanation for them is that you have a stellar mass compact object, and then you have outflows in the system. And so the outflows can explain the cause of the optical emission lines. And then they're also obscuring quite a lot of the accretion disk. And so we're only seeing one part of the accretion disk. So maybe other stuff is changing, but that's masked out and we can't see it. So this is one possible interpretation. But there's a lot of more questions that arise from this. And I think the first question is, I've talked a little bit that we can compare the globular cluster ULXs to galactic X-ray binaries, but what does that look like? Now, I did promise I would talk a little bit about neutron stars. And confusingly, we know that neutron stars can also reach super Eddington X-ray luminosities. And these ones are really hard to study and understand. And there are, more nearby sources that we can study in depth. So what does their accretion physics look like so that we can hope to disentangle them and interpret the compact object? And then, of course, are there, future missions coming up that we can use to do more of this? And then what about other kinds of star clusters? So for the rest of my talk, I'll focus on these questions. So the first question is, yes, we have actually just made this comparison. So this is work by Wasundhara Aptekorala. She is a senior at Michigan State, and her paper was just accepted last year now. And so what she did was she took a source like GRS 1915, which is a 15 solar mass black hole in our galaxy, and another black hole X-ray binary, and she compared their behavior to our globular cluster ULX. Of course, because these other sources are in our galaxy, there's a lot more detailed information, but she tried to, kind of look at the big picture trends and behavior of all of them and compare them. And so what she found is that, there are remarkable similarities, in every which way that you can make this comparison between her source and GRS 1915, which is this green point here. So you can see that on this plot where you have X-ray luminosity versus temperature, they even have the same slope. It's just that her source is quite a bit brighter. And so one thing this might suggest is that her source is more massive, correspondingly more massive than GRS 1915, which is really exciting. For a little bit about neutron stars, so there's a source called SMCX1, which is still not in our galaxy, but it's just outside of our galaxy. So it's close enough that we can do really, really detailed studies with a telescope called NICER, which is on the International Space Station. And SMCX1 gets just up to its own Eddington limit. And it has a lot in common with the more distant pulsating ultraluminous X-ray sources. And so one of these is that it has this warped and precessing accretion disk. So instead of having a flat accretion disk like in the artist representation I showed, it has changed its shape in some way. And so we've been monitoring it with NICER to figure out, does something about the physics of the system change, or is the only, indicator of variability in the system that you have the warped disk blocking out flux as it precesses? And so Rowan's results have shown that, actually the physics of the source doesn't change, and you just have the disk warping and blocking flux, which is really exciting. And so if you want to learn more about our project, which is called MOOFS, which stands for Monitoring Observations of SMCX1's Excursion, we are working on a website, and we've published 2 papers about SMCX1, and Rowan is hopefully going to get hers published over the next few months, which I'm excited about. Now, another thing that I'm interested in, of course, is finding more globular clusters. So the, sort of frustrating thing about, of course, I love globular clusters in their own right, but I think my primary interest in them is finding more globular clusters so that I can figure out, do they have ULXs in them or not? And one of the problems is that the way people find globular clusters is very piecemeal right now. But when Rubin Observatory comes online, that's going to change in a really, really meaningful way, because we're going to just have, the best, the best survey ever of the entire southern sky. And there's not only going to be, globular clusters we have seen before, there's going to be globular clusters we haven't seen before. And more importantly, we're going to have all of that information in a way that is systematic and the same. But one of the biggest issues we're going to have is that this is going to be so much data that we can't use the methods to identify globular clusters that we use now. And most likely we are going to have to turn to machine learning to help us. And so what Emma and Jeff worked on is using data that is very, very similar. It was, I think, similar to a few years worth, like a few years into LSST, and it has the same inputs as Rubin. And so they use lists of globular clusters and ultra-compact dwarfs plus contaminants, so foreground stars and background galaxies, and they ran 2 different models. So I think Emma ran a neural network and Jeff did a random forest, and then we asked it how well can it actually identify clusters. So not just how well did the model self-report as doing, but we had 2 separate lists of globular clusters. One of them was obtained through selecting them in Hubble Space Telescope. One of them was used doing photometric identification in a ground-based survey. And then, of course, the one that we trained on was a spectroscopic list of confirmed globular clusters that was completely separate of those. So we have 2 different globular cluster catalogs that are in the same data set as what we trained on, but entirely independent of how the models were trained. And it was really funny because the models, of course, said, I am 98% accurate. I am really, I'm a globular cluster finding machine. And then when we tested them on these, completely external catalogs, one of the methods did really, really well at selecting globular clusters identified in the Hubble data, and it did awful at the photometric ground-based ones. And then the other method was flipped. So it didn't reselect like 50% of the Hubble selected clusters, and then it did like 90% of the photometric ones. So when we went into this project, I was skeptical that machine learning was actually going to be useful. And I think now what I see is that I think it can do a good job, but we are nowhere near where we need to be able to use it to find clusters. So it's exciting because it means that there are exciting prospects for the future with Rubin. And so the last 3 slides I want to talk about are actually with young star clusters. So I was at a conference last year, and there was a bunch of people presenting, theory on talking about how you could form intermediate mass black hole in young star clusters. And like we have done, quite a lot of observations of trying to find or rule out intermediate mass black holes in globular clusters, but there's very, very little work done in young star clusters. And the other nice thing about these young star cluster samples is that they are at distances away from us where we can actually detect them in radio. And then we can also detect them if they are truly intermediate mass black holes when we launch LISA, which is effectively LIGO in space, it's going to be sensitive to intermediate mass black holes and ones at these distances, which is within 10 megaparsecs. So I was excited to go after these samples. And the reason why it's so exciting to be able to do radio is that if you take the X-ray luminosity and the radioluminosity for a black hole, there is this correlation. It has some scatter, but it can give you estimates on the mass of the black hole. And so you can see that this axis here, they have the black hole mass and the X-ray luminosity, and then this is radioluminosity here. And so these green points are stellar mass black holes, and they have, this relationship again with some scatter. And then over here are supermassive black holes. And this gap here where we have, 0 data points are where intermediate mass black holes could be. And so one of the things I'm really excited about is going after the young star clusters and the X-ray point sources and figuring out, could any of them lie in this part right here and, potentially be intermediate mass black hole candidates. And then of course, I also care about what kinds of clusters could host these things or have, host X-ray binaries in general. And so the nice thing about this is that all of the data pretty much exists to do that. So there is a survey that just has been releasing a ton of Hubble catalogs of young star clusters in 50 nearby galaxies. Most of these have archival Chandra data. And then because the radio is actually close enough, we can do follow-up. So I just got a VLA program approved to do follow-up on some of these. So either we're going to see compact radio jets, which are signatures of intermediate mass black holes, or almost more excitingly, we're going to see radio bubbles like this, which are probably signatures of being like, super Eddington accretion, but we only know of about, I think, 5 or 6 sources with radio bubbles, and we just don't understand them at all. So the results are just going to be very, very, very exciting. And so the X-ray analysis, I have a few students working on that. And what they're doing is they're taking the X-ray image and then detecting all of the point sources on it. So, and then, we have a list, and they're calculating the X-ray luminosities. And then we know that, we can understand the populations of X-ray binaries in these fields, and then also cross-match them with star cluster catalogs to understand which ones are the ones we want to follow up with in radio. And so I like this image here. So this is one of the galaxies they looked at. This is a galaxy image, and so a lot of them are probably in young star clusters. So in summary, it's very exciting that we have 20 globular clusters and that they don't all behave the same in X-ray. And as we're finding more and more of these sources, and there are a lot more sources out there to find, I think we're going to start to understand what is normal behavior and like which objects are strange. And then also, potentially being able to draw on the accretion physics of the systems to infer relative compact object masses. And I think the other thing I'm excited about is that in addition to looking at sources that have really, really strange accretion physics, we're going to be, pushing towards the domain of intermediate mass black holes and characterizing, all of the globular clusters that host these really, really exciting things, and then also the ones that don't have it. So if you take nothing away from this talk, the thing I'd like you to take away is that, we are working on, and we should find all of the globular clusters and all of the star clusters so that they can tell us their secrets.
Thank you, Kristen. Shall we start with questions from the audience at URGS?
Yes. Questions?
Kepler? Can you come close to the camera?
And I have many questions. The first, what you do is a cross match between cataclysmic variables and active galactic nuclei. So like the extremely variable source look like a BLX. You are looking across the jet. And it increases both the luminosity and the variability. You have observe those kinds of variability, both in the spectra and in the luminosity from VLX. So, in the X-ray binaries and the active galactic nuclei are similar in the sense that they have the disk, the hotspot, and the jet. So it's very similar. Like what you showed was the variability of the double oxygen line. The group here finds in hydrogen in the processing disk of a galaxy. So the two lines are varying because the hotspot is processing. So it's very similar. And again, the active galactic nuclei and the cataclysmic variables are the scale up of the same phenomenon, because you have to include the compact object, the nucleus of the active galactic nuclei or the accreting star in a CV, plus the disk, plus the hotspot, plus the jet. So very, very similar to me. It was exactly like all the phenomena that you saw are explainable by those kinds of situations.
Cool. Yeah, that's something that I'd be interested in following up on more as well.
Okay. You can write to me, or we can continue the discussion.
More questions from the audience at URGS or at Zoom? So I have a question regarding the 20 ULXs in GCs in early type galaxies. Were those, do you expect to find more in early type galaxies, or just where you looked at because there are more catalogs of clusters in early type galaxies?
So I think this is an interesting question, because we know that early type galaxies, have loads more globular clusters than spiral galaxies. And so I'm not sure if it's there's a physical reason why we would expect them to have more because of evolution, or if it's simply it's a numbers game of, the rate of finding a globular cluster ULX is probably like 1 in 1,000. And so you need to have at least 1,000 globular clusters for us to find one.
Okay, because is there maybe something related to the assembly history and of the clusters themselves? Because like when you look at the spiral galaxies in simulations where people have looked at the cluster systems, they have a more, the age metallicity relation is different. Like there's more variety in spiral galaxies. Maybe there's something there, I don't know.
Yeah, so the other thing, I didn't put it in.
Maybe
the angular momentum of early type galaxies allows for the formation of more globular clusters. And I think that's the reason that Kristen said the Milky Way is not a good example, because it has very high angular momentum, the whole galaxy, and therefore a very low number of globular clusters. Sorry.
Okay, go ahead, please.
So I one of the things I'm still working on is I'm putting together like basically color magnitude diagrams of all of the clusters we've looked at, with the ones separated out that have ULXs in them. And so what we found is that they're preferentially hosted by brighter clusters, which makes sense because brighter clusters are bigger and you have a higher cross section of interaction, and so like more chances to make something weird. But so far there's not a dependence on metallicity. Yeah, so it's not, so I think there are papers like Kundu 2003 or 2001 that says that, for globular cluster populations in general, there's a 3-to-1 overrepresentation of metal-rich clusters that host X-ray binaries rather than metal poor. And so far, again, it's a very small sample, and we have a lot more work to do, but so far, that result is not replicated for ULXs. The only, statistically conclusive relationship between the properties of the host clusters and does it host ULX is that they like to be in bigger, brighter clusters.
Okay. And any ULXs in M31? In M31?
No, not in the globular clusters. The only ULX in M31, there was Middleton had one, not in a globular cluster, and it was transient. And so they detected it bright in X-rays, and then it has shut off since. But yeah, so there unfortunately are no nearby globular cluster ULXs.
Okay. Any more questions? If not, let's thank Chris.